Guys, okay, so as part of these TensorFlow under the bonnet sort of codes and practices, I'm going to look into auto encoders today. Okay, so I hope that you are aware of what auto encoders are basically. So these are basically neural networks or convolutional neural networks that you are able to feed an image to, and it would take this via an encoder network into a latent space and then decode it back into via a decoder into an output that should resemble the original input. Okay, and we are going to be using the MNIST data set, but I will try to sort of go through this because the objective for me here is for you to sort of get familiar with the syntax of the coding. Yeah. Otherwise, to learn more about autoencoders, how they work, uh, really, I think you should go and do your own studies basically elsewhere regarding the theory. So my focus here is for you to get comfy with the code, okay? And especially using the under the bonnet sort of approach. So shall we say autoencoders with class. Okay. All right. So what are we going to do to start with? Let's, because we're going to be working with the MNIST data set. Yeah. I'll just already copy paste this not to waste any time. Okay. So I have import TensorFlow as TF. From TensorFlow.keras, import layers and datasets. Okay. Datasets, we are importing it so that we can extract the MNIST data from it. Then xtrain, xtest, okay, equals dataset.mnist.load data. And here we are going to make sure that we are converting this into a float32 structure that is required for the neural network. Otherwise, it would be int8, the values that are in there. And by dividing by 255, we are technically normalizing our data, each pixel in these images. Yeah. So if I run that, oh, and of course, tf.expand dimensions. This is to ensure that the shape of the input data is matching what is required for TensorFlow. Okay. So if I come and now say xtrain shape, okay. Did I put X capital X? Also use the capital X. So you can see that we have 60,000 images, 28 by 28, and they are basically black and white. Okay. Now, just so that maybe it's not going to harm it. Let's just do that again so that you understand the expand names. Okay. So we are basically expanding it, and expand themes, we are adding the necessary sort of shape that is required for TensorFlow. Okay. Okay. So, and xtest, and you should know what it is. So let's move forward. Let's just take a look at these data. So import matplotlib dot iplot as plt. Okay, and why am I doing this? Because I just want to visualize my data. So shall we look at one of these xtrains? Yeah. So which xtrain should we look at? Just have I done this? Yeah. Okay. So plt.imshow xtrain. Show me the first image. Yeah. So it is a number 5. Okay. So we have a number 5 here basically. Okay. And what else can we just look at? What is the second? Yeah, it's a 0. Okay. So we are going to be feeding these images into our autoencoder. and trying to sort of regenerate them. Okay, that's the task. But really, I want you to become, get happy with the code, basically. Now I'm going to have more efficient sort of data. I'm going to be using TensorFlow pipeline. So I'm going to say train dataset. Train dataset equals tf.data.dataset, and then call the function from tensor slices. Oh, forget these things. Tensor slices. And what do we need to feed to it? Well, we need to feed the X train. Okay, but be careful here. So train data set, I'm going to feed the train. Okay, and I'm going to actually feed the train again. We will get to this later, why I'm doing this, but just bear that in mind, yeah? That I didn't just say X train. I'm actually using two X train, okay? We'll get to that later. So, and then train data set equals, let's make a batch out of it with the batch function, train data set dot batch, and let's make it 32. Okay, remember this is an iterator, yeah? Ooh, okay, so what are we going to do now? What we are going to do is to make our autoencoder. So we're going to create a class autoencoder, yeah, and we're going to inherit TensorFlow.keras.model for this, and define init, as usual self, okay, and super, we are going to super self and then dot run init, okay. Super, let me just yeah, so then I need the parentheses, isn't it? Okay, so I've got the super. Now compared to what we did before, okay, as I said, we are going to be dealing with the encoder part and the decoder part. So first we're going to construct this, let me just bring this image. So we're going to make the encoder part first, and then we're going to make the decoder part. So we're going to say encoder, okay, and then we're going to encode it like via convolution, yeah. So I've already written this before. I'm just wondering whether I should copy paste it or should I go step by step. Well, let's go step by step maybe, or yeah, or I can do this. All right, self dot encoder. Okay, so I'll do one of them, encoder, and that's conv1. So I'm performing a convolution, okay? And when I'm convoluting, what do I do? I'm downsizing. So this is equals layers dot conv 2D, nothing new so far, 32 3x3 filters, and activation is ReLU. So far all good. Activation is ReLU, but one thing, shall we keep the shape? Okay, so padding equals same. Okay, then Let's do a max pooling after this. Okay, so self dot encoder, then max pool one, let's call it, yeah, equals layers dot max pooling 2D, max pooling 2D, layers is spelled right, yeah. Pool 2 by 2, sorry, 2 by 2, size of the kernel, and then adding the same. Okay. Then, okay, I'm just going to repeat this, except that I'm going to, okay, I'm going to reduce the number of the filters. Okay. So I'm going to just copy paste this. Sorry. So I'm going to copy paste this and make this 16. Okay. And keep that 2 by 2. Okay. So we're going to just consider this as our decoder. Now remember, this is not like a rule that your decoder or encoder should have this structure. You can be creative, okay? But just for you to understand how you do it, I mean, that you can add more stuff if you want. But I'll go with this at the moment. Now let's make our decoder, okay? Decoder. What we're going to do with our decoder, we're going to say self dot decoder and convolution 1 in this decoder equals layers dot conv to D, and we're going to go with 16 filters, kernel size 3 by 3, and activation equals, well, as I said guys, what I'm doing and the layers I'm choosing has nothing to do with a set rule or anything like that. You can do whatever you want. Padding equals same, and then here we need to upsample, right? Because we have carried out some convolutions, but we are going to be doing some upsampling. Okay, so I'm going to do self dot decoder upsample 1. Yeah, oh, good job. I just remembered that's 2. That's 2 as well. Sample 1 equals layers dot upsampling 2D, and we're gonna upsample it by 2. Okay, and then we're gonna just go back up again. So I'm going to just copy paste this now. Let's copy that. And I'm going to call this con2. I'm going to increase this to 32. And I'm going to make these 2. Okay. And yeah. So far, we are having that. But we need one last sort of output, and I'm going to make that self dot decoder output, yeah, so this is the output equals layers dot conv 2D, and I'm going to put 1 and then 3 by 3 and activation is going to be sigmoid. Okay. Padding equals same. Okay, so now we're gonna basically, now that we have returned this, so we have done this now, so we're going to now put the calls through basically for the flow of the data. Okay, and we're going to what's the best way of doing it? Let's just do it in a separate cell. Yeah, I prefer it like that. What am I talking about? Sorry. No. Let's just, sorry, I just completely went off my head. Okay. Define call, and then we're gonna say self, and as convention X. Okay. Now we are going to do partly the encoder. Yeah, so this is the def for encoder. So maybe just encoder. Okay. We're going to say X equals self dot. We're gonna call that, yeah, encoder is encoder conv1. And what do we feed into it? We're gonna be feeding that X. Okay. And then we're going to say X equals self dot, I mean, you know the drill, yeah, self dot encoder max pool 1D, yeah, and then we're gonna feed to it X, and then we now need to just feed it to the next level here, self dot encoder, no, encoder conv2D, conv2, sorry, this one. And you tell me what I'm going to be putting there is just that. Not just that, well, that. Okay. So let me see, I've done everything right. Yeah. Shall we name this just differently? Encoded. Encoded. Okay, so I'm going to name this encoded. So it's under the same call. Okay, so you see, it's not like I'm going to make one call for this or one call for that. I'm going through the same call. Okay, the same flow. I'm just making them separate by saying now decoder. So for the decoder, X equals, what do I need to do? Decoder, yeah, we need to do the decoders. X equals self dot decoder, self dot decoder, self dot decoder. Yeah. Type this up here and I forgot what did I put. Yeah, conv1D. And what do we feed into this, guys? Obviously, going to feed in the encoder. Yeah. So we are at this sort of a stage at the moment. Yeah, we are in this stage. We are in this stage. Let's just call it, I don't know. Right? As I said, all these networks are different structures, but now we have reached this point, so we are going backward now. Well, forward now. So we feed in the encoded. And then I'm going to say X equals self dot decoder. Decoder what? Decoder upsampling, wasn't it? Upsample 1, and that's going to be X. and then x equals self dot decoder underline, was it the conf2d conf2, yeah, x, and then we need to do one more upsample, right? X equals self dot decoder upsample 2. Okay, I'm gonna give x to that, and then decoded equals self dot that decoder output, which has the sigmoid function, self dot decoder output. Yeah, isn't it output with the sigmoid? Yeah. What do we feed into this? X. Okay. All right. So now that decoded, yeah. So at the end of all this, we want to return the decoded. All right. So that's done as well. Now, what do we need to do? So we have our data. Okay, we have our data. We have our algorithm now structure. All that is left to do is to go and basically play with it, right? Now let's make an instance of our code. So we're going to say model equals auto encoder, right? Model equals auto encoder, and again must be not auto encoder. That name is differently. Auto encoder. Oh, that should be right. When we get to know, probably. Yeah. No. What have I done wrong? Just a second. Well, sorry. See, one problem with copy pasting is that, okay, max pulling. I think that is it. Let's just double check. Okay, yes, it was just me being silly. So model equals auto encoder, okay, and what do we need to do now? What I want to do here, okay, what I want to do is just to go the simple way, yeah, because first I want you to have a good grasp of this. So I'm going to just use the fit method, okay? So I'm going to say our model dot compile, and then I'm going to say optimizer, yeah, optimizer equals, let's just go with Adam, okay, loss equals, let's go with MSC first, okay? So I'm going to do that. Now I'm going to fit it. So except that I think I made one big mistake, and edit runtime. So change runtime. Well, I should be on a GPU. So what I'm going to do, I'm going to switch to a GPU, okay? Because otherwise it's going to take us a lot of time to do fitting. Which now means I will need to sort of run that. Well, run everything. Okay. While we are getting the Tesla for GPU. backend. All right. So we're gonna compile the model, and now we can do model dot fit what? Train data set. So I put that time indicator as well. Okay. Oh, not bad. You know what did I do wrong? I didn't define the number of epochs, guys. So it's just going to do it once. Okay. How much was that? 1 times 16 seconds. Whereas I really should say epochs equals, let's just do 10 epochs. Now this is going to be taking some time, of course, yeah. And I think I better pause the video not to waste your time, maybe, and then come back when it's finished. Okay, so I just had to let it go. So what I want you to see here, guys, is look at the loss. It's not really changing, is it? So, and if your loss is not changing, are you learning anything? Okay. What I can tell you, no, you're not. Right. How about if you go and change this loss? Okay, so I'm going to stop this, don't waste time. Yeah. And I'm going to instead use binary cross entropy. Okay. Now what if I fit it now? Okay, are we gonna have better luck? So we just wait for this, and then I'm going to fast forward the future. As you can see improvements, right? Okay, so yeah, definitely we are seeing some form of improvement. Okay, now shall we go and see if this model is actually able to do anything for us? Yeah. Let's choose one of our just sample images. Yeah, and I'm going to say K image. Just call it image K. Yeah, this is something. TensorFlow dot reshape. Do we have X test? Let me just double check. Oh yeah, we have X test as well, isn't it? Oh, but okay, TensorFlow dot reshape. Yeah, X test, and I'm going to say number 1. Yeah, came in terms like yeah, and we're gonna reshape it to what? We go, because let's see. X test. Give me a second. X test 0. Yeah. Dot shape. 28, 28, 28. So you just need to reshape it so that it's ready for TensorFlow model. So it's 1, 2, 8, 2, 8, 4. Okay. So that's okay image. Right. And what we're gonna do, let's see, pf.im show k x test 1. So it's a number 7. Okay. Now we're gonna give this number 7 to our model to see if it can sort of generate something out of this. Well, generate something similar to this. So, and I'm gonna say reconstructed recon K. Yeah, recon K. That's a cool name. And what was our model? And what do we do? Predict K image. Okay. Now, shall we visualize or recon or pmp.im show recon K? Okay. So model.ready K image. So that's okay. I did run that, didn't I? Yeah. And I'm getting an error because of that. That's the wrong shape. Okay. I really need to return this back. So np.squeeze. Do we need to do? np.squeeze. Import numpy. I haven't imported numpy, so import numpy as np, and I'm still getting an error. Has not with np that squeeze. Oh, yeah, there's an e at the end. There we go. So, how similar are they? Well, also quite similar. Maybe the best way to do it, just so that you can see the difference, is to go a bit lower. So it's not quite the same thing. Don't be fooled. I'm just yeah, that's a good one. All right. Just look at this section here, between 2025. So you can see they're not quite the same, okay? So he has regenerated the image, but obviously there are some subtle differences. Obviously, this is a really simple image, such as a handwritten number 7. But if it was a more complicated one, you will need significantly more training and everything basically in there. The thing that I wanted you to sort of pay attention to very much was this section. Here, when we are slicing the model, okay? So we're taking X-train and X-train rather than having a label for it. Because remember, with other models, we were going by like an image goes out there, then there is an output of dog or cat, 0 or 1. Yeah. But here, we are feeding an image and we are comparing it with itself. Okay. So hence why we are having X train repeated. Because technically, as our image goes through all this process, and it's getting regenerated, you want to compare it technically pixel by pixel to the original image. Hence why we do not have a Y train as such, yeah? We have the actual whole image in there, okay? Now, obviously we could do this, I've already done that. Let me show you something else. There is a different autoencoder that I sort of created, but that was like I'm not going to write that. I'm just going to copy paste that here. So this is another autoencoder. Okay. So if if I come here and I paste it right after this, so class auto encoder, did I name that auto encoder as well? Yeah. Except that look at the code here. So instead of using, well, let me just get rid of these. We don't need to have that. So instead of using the convolutional neural network, look what I'm doing. I'm having self-flatten, I'm having encoder, and then I have dense layers, right? So these are dense layers. There's no convolution, there's no max pooling. And for my decoder, again, it's a dense layer. And only I'm doing a reshape at the end, okay? And look at the def call. So I'm flattening the input. So an image comes in and gets flattened into a single vector. And then I'm feeding it into my dense first layer, second dense layer, then the first dense layer in the decoder part, and then the second dense layer. And then we run this reshape, and I'm returning decoded, which is really the reshaped of that. So this, I hope, when you look at the code, should help you appreciate the power of convolutional neural network when it comes to computer vision and dealing with images. So now, if I make my model an instance of this model, okay, and I will be doing exactly the same thing, okay? So I'm going to be fitting the model. Let's just see how does this go. So remember, this is basically a completely different model, right? In terms of the structure. What did you have for loss there? Oh, I deleted that. I should have kept it so that we could see how the loss progressed with the other model. But anyway, let me fast forward this now. So once again, while that is running, I thought like, remember, there is no convolution or max pooling involved here. It is all dense layers. Of course, we have a flatten to convert an input image into a single vector. And we have a reshape to convert it back to an image, okay? But there is no convolution or max pooling or anything to do with the convolutional neural network model embedded in this second model. And we're just going to see how good is this. I mean, like you should be able to see from the training, okay? One of you may argue that, okay, well, if you put this for further training, yeah, of course, further training always gives better time, but let's see. So again, we're going to go with that X test. So we're going to see if your model can predict that. And K images or X test reshape, we already discussed it. So recon K is model.predict K image. So are you ready for it? Let's look. Ooh. Did you notice the difference? Yeah. How powerful the convolutional neural network model worked with sort of generating this shape out again compared to using a very basic dense layer model. Obviously, as I said, there is tons that you can do with this. Yeah, this is just out of the blue, like something simple that I packed together so that you get the idea of this. Yeah, but otherwise, uh, it just it makes you sort of realize that how powerful these models can be depending on how you structure it and how you form it. Okay. Now, of course, as usual, I have a little bit for you in case you want to sort of run this with, controlling the epochs and everything yourself. You can, okay? And I've actually written this and I'm going to copy paste it, but I'm not going to elaborate with too much. So for epoch in range, this is instead of doing a fit and compile and fit, yeah? So for epoch in range 10, for X patch, target patch. This is new, right? So I'm not saying just for X patch in train data set. This is the difference between, let me see. Mm, and, it's the other one, isn't it? Sorry. Okay. So previously we had, like in the previous video, I showed you that you go like for X batch and the Y label in train data set. But look what I'm doing here. For X batch and target batch, you might be like, what is target batch? Come on, guys. You remember the train data set is an iterator, so I'm iterating through it. But pay very careful attention here. X batch, target batch in train data set. Look at the train data set. We go back to what I previously, yeah, train data set. TensorFlow.dataset from tensor slices X train against X train. Yeah, so there is no Y label. At this point, I structured it like this because we don't have a Y label. We just want to generate the same image. Okay, so when I'm unpacking this iterator, I'm saying for X batch and target batch, technically the same thing. Same image is getting pulled out. Reconstructed image equals Auto Encoder X batch. Okay, so I'm giving the original image to the Auto Encoder and it will reconstruct an image. And then when I say loss equals TensorFlow.reduce mean. Okay, this is binary TensorFlow.cross loss to binary cross entropy. Now look at this target batch. Yeah, so I'm keeping this target batch, which is the exact same as the X batch, and I'm comparing that with my reconstructed image. I really want you to think about this because this maybe doesn't become that apparent when we do compile and fit, but here you will notice it more. So again, in my trained data set, I don't have Y labels. I just have two repetitions of the same image. So when I'm unpacking it, one is like being used to be fed into my autoencoder, and one is kept on the side to be compared with my reconstructed image. Okay, and that's my loss. Everything else is the same. So gradient equals tape.gradient loss autoencoder trainable value optimizer same. Okay, so everything else is the same. So if I run this, oh, autoencoder, why is that? Ah, that's because I named the model. Sorry, I really need to say that model. Yeah. I named it model, didn't I? Why did I put autoencoder here? Anywhere else? I think that should do it. That should do it. That should do it. Hopefully. And I don't know. Optimizer is not defined. Yes, because I haven't defined an optimizer. Obviously, when you do it like this, you need to have an optimizer ready, don't you? So my optimizer is optimizer equals my optimizer equals TensorFlow dot keras dot optimizers dot Adam. Yeah, that would be optimizer. I will spell optimizer dot apply. Yeah. Okay. Now you would also notice the difference, that when you run, when you use the fit and compile method, you will get a significantly more efficient way of your model running. So you would, I know that you're learning this, but I want you to realize that this is the idea that you know sort of what's happening under the bonnet, but obviously it's more involved. And TensorFlow compile and fit obviously even make it more efficient, in terms of how your code is run. But you would use this when sometimes you have to. I mean, later on you will realize when, like for example, for GANs, generative adversarial networks, like you would be inclined to, for example, use this because it gives you more leverage. But then that comes at the cost of sort of having your model running slower, as you can see at the moment, and I'm on a GPU. Okay. Well, I hope you have enjoyed this lecture and you have learned a few things. So, firstly, this was an experience, more sort of practice with coding, like this way, class-based, and at the same time, when you got introduced the autoencoders, as I said, you need to know the theory of autoencoders before watching this video. But once you know that, then you can go and play about with, the structure of your autoencoder. You can do many things. Yeah, this is like just simple out of the blue that I've just created. Yeah, it's not the best, it's not the most efficient, it's just that. Yeah, but I hope that it has given you the appreciation of knowing how powerful these models can be based on their structure. And also, of course, for autoencoders, I really wanted you to understand that we are not having a Y label. We are not having an output as such. The output is the original image intended to be. Okay. So we're comparing the output with the input for our loss. That's very important. Yeah. So um, just bear that in mind. Okay, I'm actually going to stop this now. So it's the same thing, it's just slowing, running slower. So I hope you have enjoyed this lecture and keep on practicing.